So we're going to start just reminding ourselves what the binomial probabilities are. And it's kind of an extension of ideas we saw at GCSE. So where we did tree diagrams at GCSE with only two outcomes, this is effectively what a binomial expansion, or sorry, binomial probability is an extension of. So if we take a random variable x and it can take a range of particular values in a sample space, and basically what we're looking at is discrete random variables. So actually in this case, normally only whole number values like amount of cold calls that turn into sales or that sort of situation. So this is what discrete means. This is a key difference from the normal distribution, is that it can only take certain values. And you might think, yeah, I'm fine with that. I know when it's binomial, I know how to spot it. But we're going to look at the notation carefully as well. So the binomial distribution is basically used to estimate the probability of the number of successful outcomes in multiple trials. So the reason that this is an extension on tree diagrams from GCSE is you don't want to draw like a 10-branched set of tree diagrams. You just want to understand the process. So the notation we use is we say that x, the random variable, follows a binomial distribution with n, the number of trials in total, and p as the probability of success of each trial. So this is probability of success of each trial. So n was number of trials. And people do find this notation a bit weird. And they kind of think, how do I even say that? So we say x follows the binomial distribution with n number of trials and p is the probability of success. Now, another question they love to ask is actually the conditions under which the binomial distribution is appropriate. So these are the kind of 4 conditions that we want to know, and we want to be really confident with these. So first of all, the fact that it's called the binomial, referring to 2, there are 2 possible outcomes, success or failure. There has to be a fixed number of trials, so n doesn't change. The trials need to be independent, so every time it's a new go, same situation again, it doesn't remember what happened before. And the constant probability is the final crucial thing. So the chance of being successful each time does not change. It's independent. It doesn't have a memory of what happened before. So these are the conditions under which it's appropriate to use a binomial distribution. So make sure you know them. And we don't want to forget any of those because we're often asked to explain why it's appropriate. Conditions for binomial. Okay, so let's push on and look at the actual formula for doing this. So sometimes people see this formula and they think, oh, this looks really awful. And am I giving it? Can't I just use the calculator? Absolutely. Most of the time you are going to use the calculator for this, but it is quite good to understand where this comes from. So we have this as the binomial coefficient, and you recognize it from pure maths as well. For when we do binomial expansion. And then what we also have is if we actually look at what the binomial distribution is doing, is there's kind of 3 distinct parts. And this is where I put this in the context of a massive epic tree diagram. If I have 10 branches and I want 7 successes, it's like win, 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 win 7 times and lose, lose, lose 3 times. So you times the probability of success to the power of how many wins, multiplied by the probability of fails to the power of how many fails there are. And of course, because there's so many different combinations, that's why we times it by n choose r or n choose x. That coefficient, that binomial coefficient, tells us how many ways there are of arranging it. So what this gives us is the number of ways of arranging basically X amount of successes in N amount of trials. You know, when you have a long day and you think, have I spelt successes right? I think there's a lot of double letters there. I think that's right. Anyway, you know what I mean. That's good. So N amount of successes, sorry, X amount of successes in N trials. Then what we've got very simply is probability of success of the amount of successes we want. And I'm not going to say of success, I'm going to say of successes again. Hoping I've spelt it successfully. And then this will be the probability of failure. And we're kind of timesing it all in. Okay, right. So, for example, and just make sure we're happy with that choose notation on the calculator. So 3 choose 2 ultimately works out 3 factorial over 2 factorial, 1 factorial, 3 minus 2, which come out as 3. Okay, 6 over 2. Now, let's push on with this and let's look at this question here. So we've got a 4 marker split into 2 marks. Greg and Tim are playing a game of Yahtzee. The game lasts for 13 turns. On each turn, Greg and Tim both throw 5 6-sided dice to try and match numbers they roll. So on his first turn, Greg manages to get a Yahtzee, which means all 5 dice have the same value in a single throw. Explain why the probability of this happening is 1/6 to the power of 4. And the second question says, over the course of the game, Tim manages to get a Yahtzee in a single throw 3 times. Calculate the probability of this happening. Your answer should be given to 3 significant figures. Now, a few things to consider. The key information in the context. We've got to think about why this is 4 and not 5. So that might be quite kind of key to think about. Remember to round in the correct way. And there's lots of key information here. So do start this ahead of time already. I will work this through with you. It's an explain why. So look out for that command word. We need like 2 marks of reasoning. Probability. This is the thing we're looking at. Understand the context that all 5 dice have the same value. 13 turns. 5 6-sided dice. And then we're going to have a little look. So this is tricky. And this is the kind of question that I would feel a little bit kind of, oh, there's too much to take in information here. How am I going to do this in a couple of minutes? It is quite daunting. The second part is just to calculate, though, 3SF. So we'll start working this through together shortly. I'll just give you a minute to kind of digest that. And well done if you've already made a start. Okay, so we'll start looking for it straight away. For part I, where we're looking to find the chance of all 5 dice having the same value, what we need to interpret is what's happening. So each die is independent. First die can actually have any value. So when you were looking at it and you're thinking, why is it 1/6 to the power of 4 and not to the power of 5? Well, weirdly, it doesn't actually matter what we throw first. It matters that all the others are the same as it. So the next 4 must actually match this value. So the probability of each die matching that first die's value is 1 in 6. So what we've got is 1/6 times 1/6 times 1/6 times 1/6, which is a 6 to the power of 4. Now, this was an explain why question. And for those that attended the session yesterday, we set this out very sort of similar fashion. We want to kind of deductively go through and say, well, this is what I know. This is what it tells me. This is the probability. So this is how I combine it. And then it's quite conclusive. And going through that thought process can actually help you work it out. So yeah, the context we had to realize was the first one doesn't matter. And because it was a show that, we could have almost made that leap and got that ourselves as well. So well done if you followed that. The next bit, let's do a bit of calculation. Oh, sorry, yes. So because it was a sixth times a sixth times a sixth, and they've all got to do that, you could have also thought of it as 6 times all of it times together, which would have cancelled to the same thing. I think this was more logically how we discussed it. Okay, but it is effectively the same as the calculation at the bottom there. Right, let's do part 2 of the question. So this one, we want to work out the chance that it happens 3 times. Now, the results of the die are discrete outcomes. There's 2 outcomes, Yahtzee or not a Yahtzee. This is very common, actually, that they'll use the first part of the question to inform the probability for the second part. Now, it is a fixed number of trials, and they are independent, and the chance of a Yahtzee is always the same. So we are actually establishing a binomial distribution here that's pretty involved and just directly comes off the back of what we just did. Okay, so we're creating a binomial within question 2. So what we know, just check that that fits the framework for a binomial, is there are 13 turns for this part of the question. So 13 chances for success. So 13 is therefore n. Now, the chance of throwing a Yahtzee is basically the probability they gave us, they gifted us in part A. So 1/6 to the power of 4, which you could work out if you wanted. You got your calculator, you could give that as a fraction, 1/1296. That's the probability of a successful Yahtzee. Then what we're going to do is we're looking for the probability of exactly 3 in 13 goes. So this means the number of successes is 3. So n is 13, x is 3, and p is 1/1296. Now, for some of you, you can plug directly into that formula. Many of you are very confident with your calculator and recognize that you could use the binomial PD function, not the cumulative. We're not looking for a tail of events. We are looking for a specific event, which is this particular value. Now, this formula will work perfectly, but why not make the most of the calculator that will just do that for you? Because we should get the same outcome. And actually, if you've got 2 ways of doing it, even better. I'm going to anticipate it's a very small number. So we plug those values in, got some tiny numbers in there. And our final answer, the chance of getting 3 of those in 13 goes is 1.3 times 10 to the minus 7. So ridiculously small. Very, very unlikely. Okay. So well done if you also used the PD function for that. That was really good. What we're going to push into now is using the cumulative binomial probabilities, because this will help us later for hypothesis tests. So a cumulative